So hello everyone, welcome to the lecture, and as Jesse said, today's lecture is going to be about modeling to generate alternatives and how we can use it for power system planning. Um, so for the outline of this lecture, we'll first again go through the challenges for capacity expansion planning, different types of uncertainties, we already talked a bit about that before. Then we'll go through different formulations for MGA. Um, we'll go through the example problem that we went through for the last lecture, and then we'll talk about a case study for the American West. Okay, so to start this lecture, I first wanted to show this one slide. This is the work done by Evelina back in 2016. So what you see here on the left-hand side of this figure is the cost optimal capacity expansion plan for the UK energy system. So this is how they should have expanded their power system if they only thought about the cost optimal solution, right? But on the right hand side, as you can see, in the last 10-15 years, the capacity expansion has kind of deviated from the cost optimal solution. So what this figure basically tells us is that what happens in the real world is not necessarily the cost optimal solution, right? So the black line here is the cumulative total system cost for the cost optimal solution, and the one here is for what the cost was in the real world. And if you look at the difference between those two costs, it is the real world solutions are usually around 10 to 20% more expensive than the cost optimal solutions. So this basically kind of asks the capacity expansion problems models that we have been formulating to not only consider the cost optimal solution, but also look at other objectives that might help us understand um, how the power system model should develop as we go ahead. All right. So we all obviously know about power system capacity expansion models, and the goal of these models is given in these 4 points. So first, they have to consider many different kinds of physical constraints, policy-related constraints, resource availability constraints, etc. Second, they have to provide kind of a methodological framework so that we can give some kind of prescriptive analysis that supports decision making for policy development, right? Third, whenever we provide these insight or this prescriptive analysis, it has to be somewhat robust so that we can implement it for the policy implementation. And fourth, we have to maintain internal consistency in the model when we evaluate the future scenarios. Now, the biggest challenge in the power system capacity expansion models is that we have to meet all of these objectives, and we have to meet them at a reasonable computational cost, right? And while meeting these objectives, we have to consider parametric and structural uncertainty. So if we do not consider this uncertainty, then we might give policymakers some solution, and we might give them a false sense of precision in that one model solution, right? So to avoid this, we have been using some uncertainty analysis techniques, and we talked about two uncertainty analysis techniques in the last lecture on the last Monday. Those were robust optimization and stochastic linear programming. So those techniques work very, very well when we have a small set of uncertainty, or we precisely know the preferences of the small set of clients, right? So a client might want to know what happens to the energy system if solar PV cost goes from plus minus 20%. So that preference is very well known. So that preference can be easily modeled with SLP or robust optimization. But the problem or the downside of these formulations is that they kind of fail to consider many different divergent values or interests of the different actors in the um, electricity system, power system model in reality. So what we are going to do in this lecture is we are going to apply this modeling to generate alternative techniques And we are going to understand how this technique can respond to the structural uncertainties in the model. Structural uncertainties arise from, again, the fact that we cannot exactly model the real world process. For example, if I don't like nuclear, for example, right? So this model does not exactly, we do not exactly model my preference in our solution, in our power system models. The power system models that we have right now, they only consider one system or one decision maker who can make a cost optimal decision, assuming that they have perfect foresight about what is going to happen in the future. But in reality, that's not the case, right? So we have to consider these different preferences from different actors in the system. All right. So talking about MGA, it was first developed back in 1982 by Dr. Brill. He was actually the one who introduced me to energy system models. And MGA was then first introduced to energy system models in particular by Dr. DeCollis, my advisor, back in 2011. So the objective of this algorithm is to find solutions that have similar objective or similar total system cost, but have maximally different system composition, right? So to achieve these objectives, people have come up with many different ways to formulate a problem. And to formulate this problem, we divide the existing formulation into two groups. One is the linear programming formulation, and then the second one is mixed integer linear programming formulation. So we are going to talk about these four formulations today. Hop, skip, jump, and the heuristic formulation falls under the linear programming formulation category, and the maximizing absolute difference and integer constraint para formulation, that one falls under the MILP formulation. So the rest of this lecture is going to have a lot of mathematical formulations. So at any point, if you have any questions about the definition of a variable or about the definition of a constraint, then please let me know right away, because we are going to be building on one solution on the other. Okay, so just before start going through all of those formulations, just talking about the basic idea of modeling to generate alternatives. If we have a problem of this format, we are minimizing Cx, where assume that C is your cost function, subject to Ax equal to B and x greater than equal to 0, and assume that x1 is an optimal solution of this problem. So the idea of MGA is basically to create a bubble around the cost optimal solution. So if this is a feasible space of this problem, and if this point represents the least cost solution, then modeling to generate alternatives systematically explores this near optimal space so that we have maximally different solutions. So for example, this solution right now is maximally different from the least cost solution. So MGA finds out ways so that the cost of these solutions is similar to the cost of the least cost solution, but the value of the solution is way different than the least cost solution. So what we do is we reformulate the original problem so that we maximize now the distance between the new solution from the previously optimal solution. Right? So we are minimizing the absolute value between x, which is a variable in this problem, minus x1, which is optimal solution of the original problem. And we are adding another constraint here, more apart from the Ax equal to B constraint. So this constraint says that our current objective value, or our current cost, total system cost, should be equal to the cost of the previous solution, the cost of the least cost solution, plus some delta, which is we are adding some slack. So what this formulation is saying that we want to find out maximally different solution so that our cost is, say, X% or delta percent more than the least cost solution, right? So this solution to this problem will give us the first MGA solution, or the solution that is maximally different from the least cost solution. Now to find out second solution that is maximally different from both of these solutions, we reformulate the objective function so that now we maximize the different distance from the original solution and from x2, given that x2 is a solution of this problem, right? So the constraints remain the same in each iteration, but the objective function will keep on evolving. So that is it. This is MGA, right? It looks simple to look at just for the formulation, but the problem with this formulation is that we have absolute value function in the objective, right? So that fact makes it very difficult to solve such kind of problems. So now whatever formulation we are going to go through, the 4 formulations, are basically a way to simplify this problem or to approximate this problem, right? So first we'll go through a formulation given by James Price. This formulation gives exact solution for maximally different, for finding maximally different solution portfolios or technology or solution options. So what this formulation does is it introduces a dummy variable alpha in the original, in this problem. So it converts this objective in the form of a constraint by introducing a dummy variable alpha. So we are now maximizing alpha such that alpha is less than equal to this distance. So to simplify this constraint, which has absolute value function, we split this constraint into 2 parts, right? One is this one and the other one is this. And we introduce a binary variable y1, which can take a value 0 and 1. And we introduce a big M. This method of splitting the constraint is called big M method. We introduce a parameter big M, which takes a large enough value given your parameters in your problem, right? So if at an optimal solution, if x is greater than x1, sorry, if x is greater than x1, then y1 is going to take a value 0, right? And then alpha, the value, optimal value of alpha will be x minus x1. If at optimal solution, if x is less than x1, then value of y1 will be 1. And the optimal value of alpha will be x1 minus x, right? So if we get a solution for this problem, then the next iteration of MGA, we add 2 more constraints and 1 more binary variable. So we will add another binary variable here, and these will be 2 more constraints. So the downside of this formulation, as you can see, is that whenever we have integer constraints or integer variables in the problem or binary variables in the problem, the real world formulation of this problem becomes too difficult to solve. The problem becomes too computationally expensive. So in this method, we have to add 2 more constraints that contain binary variable and 1 binary variable for each MGA iteration, right? So now, because this is too difficult to solve again, we have a hop, skip, jump formulation, right? So the idea behind this formulation is that if we have a solution x1, which has, for example, say I variables in total, this x vector has I components, and say x1 takes a positive value and all of the rest of the variables takes value 0, then what this formulation does is it minimizes x1 subject to the same constraint. So idea behind this formulation is to get rid of or push away from the variables that have already appeared in the solution. So in the next iteration, if say x1 takes a positive value in the first iteration, and if x2 takes a positive value in the second iteration, then in the next iteration, we will minimize both x1 and x2. Make sense? Okay. So this formulation is great.
Sorry, Neha, could you
Yeah.
explain again, like the 8?
Right.
I kind
Okay.
of.
So I1 is a coefficient that we set to 1 if xi1 is positive, right? So if in the solution of this problem, if x1 at optimal value, if x1 takes a value 1 or takes some positive value.
Oh, so are you just trying to remove all the, like, so you remove all like the unnecessary?
Yeah.
Okay. Okay, I get it.
Yeah. So we are just trying to push away, we are just trying to tell the model to minimize using this solution, minimize using this x1 variable because it has
Right.
already appeared before.
Right. Okay.
Yeah.
Thank
Okay.
you.
So this formulation is good because it is linear, because it is straightforward, does not add too many constraints, it just keeps on modifying the objective function. It's good enough for some problems, but the drawback again for this formulation is that it quickly saturates because we are kind of trying to push away the variables that have appeared before. The diversity of solutions that we get from this formulation is much lower than actually maximally different solutions. So then we have one more formulation, which is integer cut constraint formulation. So for this formulation, the idea behind this formulation is that if you have this one solution, then we want to push away from the solution. So this formulation applies only when we have binary variables, right? So if x belongs to 0 and 1, then only this formulation works. If we have integer variables, we can convert those variables into binary variables and then apply this formulation. So we again form two sets here, I1 and I0. This I1 set is a set of all xi that take value 1 at the optimal solution. And I0 is a set of xi that take value 0 at the optimal solution. Right? So the integer cut constraint formulation then introduces this one constraint. What this constraint is doing is it is telling us to find at least one xi that previously has value 1, and we are trying to push at least one xi away from that solution. So this xi1 minus xi for this set, and we are summing it over, which means that we want at least one xi that previously took value 1 that should now take a value 0. Or we want at least one xi that previously took a value 0 that should now take value 1. So we are trying to exclude the solution that we had before. So this constraint makes the previously obtained solution infeasible. Does that make sense? Okay. So if the solution of this problem is x2, then we will just add one more constraint here, which will try to push away from the second solution, right? So the good thing about this formulation is that we do not add any more variables than we already have. We only keep on adding one constraint for each MGA iteration. Right? One thing again to note about this formulation is that we do not specify a slack constraint. So we do not have any bound on what our objective value should be. Instead, the stopping criteria for this formulation is the number of iterations, or if we repeat a solution again, then we stop this formulation. Right? If you want to simplify this constraint, then the simplified formulation is given here. Okay. So now all of these problems have some form of drawback. Either they are too computationally expensive, or they do not provide diverse enough solutions, right? So we move to the fourth formulation, which is the heuristic formulation. The idea behind this formulation is that, okay, we cannot use integer cut constraint, or we cannot push away from the existing solution. So what we do instead is we explore this near optimal feasible space randomly. And once we have all of these points, we save those points, and then we try to find out which of these points are actually maximally different from the original solution. Yeah. So now the objective function becomes maximize beta into x subject to the same constraints. And k is the number of iterations we are planning to take, or number of MGA iterations. So if we have 10 solutions in this feasible space, then we will run this we'll solve this problem 10 times with 10 random set of this parameter beta. Next, we solve this problem with the minimization objective, because our objective is to just randomly search this space. So once we have optimal solution of this problem, which is xk max, and optimal solution of this problem, which is xk min, we then club them together and put them all in this set, right? So now we have a set of all of these parameters, and we want to find out a solution that is maximally different from the least cost solution. So what we do is we find Euclidean distance from the least cost solution, and a point which has the highest Euclidean distance from the least cost solution will be selected as the first MGA solution, right? Then we put that solution in this set S select. So S select will now have two solutions. The first solution will be the optimal solution of the problem, of the least cost problem, and the second solution will be the one with highest Euclidean distance from the optimal solution. Next, if we want to find the second maximally different solution, then we calculate this, which is called harmonic mean of squared Euclidean distance. So what this is trying to do is trying to find the Euclidean distance of all of these points from both the previously selected points, right? And it excuse me, and it gives us the next MGA solution. Okay, so now that we have gone through all the solutions, all the formulations, just want to take a quick break and see if anybody has any questions or comments. Okay. Um, all right. So you're going to have to formulate some small problems. So keep your pen pencil ready. We are going to go through the same example that we went through last time and try to formulate just some one of these formulations, two of these formulations. Okay. So last time we went through this problem for our stochastic linear programming formulation and robust optimization formulation. Um, so we had Mr. Z who had 3 generation options. He could use solar PV, or he could use wind turbine, or he could use gas generator for satisfying the electricity demand. And we knew that each of these technologies, they had pre-specified amount of profit. So these were the ranges of uncertain profit parameter. But right now, I'm just giving them here just for reference. We want to formulate a problem using these values, the nominal values, and the objective is to maximize profit subject to the resource availability constraint. So I will just give you a minute to formulate this problem, just simple maximize profit subject to the constraint. Yeah, so the formulation is then just maximize 45 into x1 plus 35 into x2 plus 50 into x3 subject to x1 plus x2 plus x3 equal to 1, right? And all of these x1, x2, x3 have to take value 0. So now that we have the formulation, anybody wants to take a try at finding the optimal solution?
All x3.
Yeah, okay. So our optimal solution is just 0, 0, 1. So we want to build all x3, which maximizes our profit, which is $50, right? So now we want to find out a first maximally different solution. And we are assuming that Mr. Z is willing to let go of 20% of his profit. So when we were thinking about the first MGA formulation, it was in terms of cost, right? We were minimizing the cost. So the slack constraint was set such that we do not want to so the maximum cost that we have available is optimal cost plus some slack value. Here we are talking about profit. So we want to model it as Mr. Z is willing to let go of 20% of its profit to seek maximally different solutions. So we will first formulate the problem for just the basic MGA formulation. So again, anybody wants to take a guess about what the formulation would be? Maximize the difference between the new solution and the previous solution. And this here is in terms of cost, but we want to think of it in terms of profit. So what would be the MGA solution, MGA formulation for this, for the problem that we are talking about?
So x1 would be 0, 0, 1.
Right.
And then the delta is based on the 20% of profit that he's willing to lose, right?
Right. So then the formulation would be just x1 minus 0 plus x2 minus 0 plus x3 minus 1. And all of these are absolute values. And the slack parameter here is then whatever your cost objective is, or the profit objective in this case is, has to be greater than or equal to 50 minus 20% multiplied by your previous objective value. So again, anybody wants to take a guess about what the solution of this problem would be? It's not too straightforward, but still straightforward enough. Solution for this problem is 1, 0, 0, which is we decide to build x1, right? So the objective function value right now will be 1 minus 0, which is 1, and again 0 minus 1, which is 1. And the profit at the current solution is 45. So this formulation is still simple enough that I can guess the solution of this problem. But if we try to find a solution that is now farther away from both of the solutions, which is MGA1 and the least cost solution, then the formulation again becomes like this. So we are only modifying the objective function. In the first part of this objective function, we are trying to push away from the first least cost solution, which is 0, 0, 0, 0, 0, 0, 1. And we want to push away again from the second solution, which is 1, 0, 0. Right? So just looking at this problem, it has just 3 variables. It has only 2 constraints. I have spent half an hour on trying to solve this problem just by looking at it before this lecture. But if any one of you try to solve this problem or just see the solution right away, then please let me know. But the point of this problem formulation is that just by looking at it, it's not easy to find the solution, even if the problem is small enough or easy looking enough, right? So then we want to move to a next formulation that simplifies this problem and makes it easier to solve. Okay, so I want to again give you a minute to formulate hop, skip, jump formulation for our two MGA solutions. Oh, sorry, two solutions. So we have a least cost solution, which is 0, 0, 1, and we have first MGA solution, which is 1, 0, 0. So I want to give you a minute to formulate the hop, skip, jump formulation for the same solution. For now, we want to find the second MGA solution. So how would we modify the existing problem formulation based on this? Again, anybody wants to take a crack at it? X3 has occurred before and X1 has occurred before. Anybody wants to guess?
Is it minimizing x1 plus x3?
That's correct. So we minimize x1 and x3, x1 plus x3, subject to, again, the same constraints, right? So suddenly, this complicated formulation became much easier to solve. And just by looking at it, we can see the solution of the problem. The objective of this is basically to maximize x2, so that because it does not appear in the objective function at all. So it might not be too straightforward, but the solution of this problem is relatively much easy to solve. So x2 does not affect the objective function, so we want to maximize x2. And with this hop, skip, jump formulation, the second MGA solution is 0, 2 by 3, 1 by 3. And the optimal objective function value here is 1 by 3, and profit at this current solution is $40, right? So this might not necessarily be the actual second maximally different solution. So we try to formulate another formulation. We try to use another formulation to find out if this solution is actually the second maximally different solution. Right? So using James Price's formulation, we create two new variables. The first variable corresponding to our first MGA solution, first least cost solution, and the second variable corresponding to our first MGA solution. Right? So I'm not going to ask you to solve this problem. It's complicated enough. But if you want at home, you can solve this problem and see if the solution to this problem is equal to the solution of the MGA second MGA solution that we computed from the hop skip jump formulation, right? You can also again modify this problem to solve for the third maximally different solution. Okay, so now that we have gone enough through the case study problems and through just going through the problem formulation for a small case study, let's talk about the use of this MGA algorithm for a real world problem.
Can I ask one question, please?
Yes, sure.
On the previous slide, I'm sorry if this is silly, but how do you decide, how do you choose like Y1 and Y2? Like what determines whether it's one or zero, whether Y1 or Y2 is 1 or 0?
Right, okay, that's a good question. So Y1 and Y2 are variables in this problem.
Okay.
Right, so the problem solution is going to determine whether Y1 should be 1 or 0.
Mm-hmm.
But in general, if you look at just these two constraints, if Y1 is equal to 1, because our M parameter is big enough, this constraint becomes redundant, right? Because alpha has to be less than equal to this value and alpha has to be less than equal to this value. So if we set Y1 equal to 1, it makes this constraint redundant, and alpha will be set equal to x1 minus x, because 1 minus y1 in that case will be 0, and this term goes away. So depending on whether x1 is greater than x or whether x is greater than x1, it will determine the value of y1.
Got it.
Yeah. Okay. Any other questions about any of the formulations?
Yeah, Neha, I was wondering, instead of bringing in the big M and the integer decision variable y1, why wouldn't I just simply put, because there's a absolute value across x minus x1, so why can't I just make it like alpha less than equals x minus x1 less than equals negative alpha? Or I'm probably saying it the other way around. No.
That's again a good question. So if we just
I
remove,
will split it into two inequalities, but I mean, that can be done even without invoking the big M and the additional integer
Right.
variable, right?
Okay, so we have tried that. If you get rid of both of these components of these constraints, what is essentially going to happen is alpha is going to, for example, okay, let's see you do not have these two components and optimal value of x1 is 1. Okay, just for example, assume that x1 is 1. Now we want to maximize alpha. So alpha has to be less than equal to x minus x1, which is x minus 1, and alpha has to be less than equal to 1 minus x. Right? So let's assume that the actual maximally different solution is 2, x equal to 2. So in that case, alpha has to be less than equal to 2 minus 1, which is 1, and alpha has to be less than equal to 1 minus 2, which is minus 1. Right? So in that case, the maximum value of alpha that satisfies both of these constraints will be minus 1. Right? But if you set value of x equal to value of x1, the maximum value of alpha will be 0. Yeah. So if we do not consider these components, one of these constraints would not become redundant, right? So if one of these constraints is not redundant, then alpha will take a value of 0 by setting value of x equal to value of x1, because if it doesn't do that, the optimal value of alpha will be negative. Okay. So moving on to a case study that we recently did in the Zero Lab. We basically wanted to know how, what different land use options we can find based on different renewable energy development options, right? Because if you want to develop solar or if you want to develop onshore wind, it is going to take some land. It is going to require some land. And even if the land has conflicting objectives, for example, if that particular piece of land has great resource quality for solar and wind, but if that piece of land also has some other goals or other conservation goals or other objectives, for example, this land might be used as a beach, right? So if there are these two conflicting objectives, then those are usually not taken into consideration. So if we use the current capacity expansion models, they usually base their decision on the resource quality. So they will ask you to build a solar PV or wind technology on land where you have the highest potential resource quality, or the LCOE of that particular site is lowest. But as we saw, in reality, the least cost solution might not always work, right? So if we use these models, then they will be developing or they will be providing us solutions that asks us to develop renewables in land areas that might have very high potential, resource potential, but might also have very high conservation value, right? So that can create a conflict between renewable energy development and land conservation goals. So we need to know what different options we have that does not necessarily affect, again, our cost objective, but lets us consider different objectives in the system that are not necessarily modeled in our problem formulation. So for doing this, we use a GenX capacity expansion model that we frequently used in Zero Lab. And this model has 5 cost objectives, right? So it has fixed and investment cost. It has variable and fuel cost. It has cost of non-served energy, startup and shutdown cost, and it has transmission cost parameter. So I again want to give you guys a minute to think about how we can reformulate this objective function to explore our land use potential goals. So what different MG objective function can we formulate? I'll start with one. For example, we can find out maximally different options for technology capacity, right? So for example, we want to find out options that maximize distance between capacity expansion for a particular resource. We want to find capacity expansion option that has maximally different solar capacity, wind capacity, or other capacity options. So can you guys think about any other objectives that we might want to use here?
You could do like maximally different location of new build if you're concerned about like where jobs are going to be created.
Mm-hmm. That's a good one. Anything else? we do not necessarily have to rely only on the cost objective as well. We can also find out what different emission levels can we achieve. So for example, if the objective function or the optimal solution achieves X amount of emissions or like reduces emissions by X%, then we can also find out what different technology portfolios we can have to have maximally different emission levels. Any other idea about modifying the objective function?
We also think about like the location of the emissions, because we might be concerned if they're near cities, for example.
Yeah, that's a good one. Yeah. Okay. So for this case study, we focused on maximizing power generation by technology type and by region. So where we are developing that technology and what type of technology we are developing. So both of those we want to find maximally different options for. So we use the heuristic formulation that we talked before, and we find or we solve this problem around 200 times with different set of this beta parameter. And we set the slack parameter to 5%. So we tell the model that we are okay with 5% more expensive solution, right? So using this formulation, we then find out 5 different MGA portfolios. Why we choose 5 is because we, as we discussed before, we compute harmonic mean of squared Euclidean distance for each of those solutions. And then we find out that for the 6th MGA solution, the amount of diversity that we get, or the unit or the increase in diversity that we get from 5th to 6th solution is relatively low. So we decide to only consider or only explore the first 5 MGA solutions. We apply this formulation then for the American West. So we divide this WEC energy system into 6 zones. And for each of these zones, we assume that the transmission is given by the transmission within the zones is not constrained, but transmission between the zones is constrained. We have solved this case study for 3 different technology availability options and 2 different level of electrification of the system, which is high electrification by 2045 and reference electrification level by 2045. The objective that we want to achieve here is 100% carbon-free electricity supply by 2045. And then we find out maximally different land use options across the American West, right? So instead of presenting all of our results, I am only going to talk about the results for high electrification scenario, and only going to talk about a case where all the clean technology options are available for capacity expansion. Okay, so for capacity expansion results, we have a base case scenario here. And then we have 5 different MGA scenarios. Now, in this figure, we have total capacity in the entire WEC, or in the entire Western Interconnect. So now, as you can see here, it's not very different, right, from the base solution. It looks quite similar. But the point to note here is that we have 6 regions and we have multiple states in those 6 regions. And the capacity that we want to expand for a particular resource overall might be similar to the base case level, but where you want to build that capacity can change drastically. So this figure here shows you the land use for solar development in all of the states in the Western United States. right? So for example, for California, in the base case, land use is this much, but then we have many different options which have varying land use for the California region. So this allows us to kind of find a trade-off between what happens if California does not have enough land for developing solar for developing solar PV in that region. Similarly, we have similar figure for land development. Land use for onshore wind development, and in general, so onshore wind development has higher flexibility within the regions. Right? So as you can see here, one thing to note is that the land use for solar PV is much higher, is significantly lower than land use for onshore wind turbine when we consider the site-wise boundary of that solar PV or onshore wind development. But one thing to note here is that if we just consider the footprint, then out of this area, for solar PV, we almost need 90% of the area, 91% of the area will be the footprint of solar PV, new solar PV capacity. But for onshore wind development, we only need 1% of the total area that is used as a footprint of wind turbine, right? So rest of the area, so that accounts for just 400 to 500 kilometers square for onshore wind development as compared to 20,000 kilometers square, or 90% of 20,000, which is around 18,000 kilometers square for solar development. So we have to consider these trade-offs, that even if you need this much land for wind capacity development, you still can use the land on which you have developed onshore wind for other purposes, not just for producing electricity with wind turbine. We have kind of downscaled these results to find out exact locations based on their LCOE on where you should be building solar PV in the American West. These are our recent results. We still need to refine them a bit, but I just wanted to give you an idea about what we can do or what MGA solutions can give us for analysis or for policy analysis, right? So these are the solar sites on which we can develop. These are the sites on which we can develop solar PV. And if the site is darker, then it means that that site occurs in more solutions. If this area is lighter, then it means that it occurs only in 1 or 2 solutions. So we have 6 occurrences here, 6 for one base case solution, the least cost solution, and 5 for 5 MGA solutions, right? So if for this site, it basically means that this solution occurs in all MGA solutions. So even if you had a 5% more budget, building on this site is a very good idea, right? It kind of is a robust idea considering that we have enough budget. But this site, for example, occurs in just one MGA or one solution, right? So people in this area might have concerns about developing large solar PV farms near the city, right? So in that case, we can find out what other options we can have for solar PV development. Similarly, we have sites for onshore wind. So there are these sites near the beach, right? Near the coastline. And there might be some people who might not want to see wind development over there. So in that case, MGA solution allows us to find out what other solutions we have in a similar cost range that will again satisfy the electricity demand that we have. All right. So I want to finish up with just asking you guys what we learned throughout this entire exercise and what did you understand from this. So I'll give you a second to kind of summarize what you learned.
I found it very interesting because I think with small, like the political feasibility of two different options could just be totally, honestly different, even for like, so almost like the cost difference is irrelevant in those cases, but looking for the best of both worlds is obviously something we want to do with our research.
Yes, that's a good point.
I'm curious if there's any downside. I mean, aside from just having to run more models and spend more time on it,
Mhm.
it seems like there's no bad things that could come from doing MGA.
One thing to note is that if you provide somebody with too many options, it just the entire purpose is nullified of this formulation, right? Which is why we kind of restrict the options to only 2 or 3 options. Even 6 options is probably too many for analyzing the policy. So it's not a downside, but we have to be careful about how many solutions we present for a particular policy. We cannot just present 200 solutions. And I mean, we can, but that would just defy the entire purpose of the analysis.
Yeah, I think you heard something similar from Aaron last lecture as well about multi-objective optimization, where you can technically optimize across n dimensions, but typically people have a hard time understanding more than 2 trade-offs at once.
Yeah.
So they kind of have to prioritize what do they care about most, and then look at those trade-offs and kind of ignore everything else.
Yeah.
So yeah, figuring out ways to deal with the raw data that you get out of this kind of approach, as well as any kind of global sensitivity analysis approach as well, is quite challenging, and where a lot of kind of careful work needs to be done if this is actually a useful decision support tool.
Yeah. Any downsides about the current models and how we are using them? How we should not use the models? One thing that I have learned through this entire exercise and through the modeling of stochastic linear programming, robust optimization, and MGA is that whenever we have a lot of uncertainty in the future, we should not be using these models for making projections about how the future looks like, right? If we just come up with one single projection about how the future looks like, it has a very high probability that it's going to mislead some of the decisions. So instead, what we should be rather using the models is for systematically searching kind of the decision space and generate insights about what structural uncertainty we have, what solutions addresses that particular uncertainty, and just in general providing robust insights that do not necessarily change drastically with just small change in one parameter. Right? As Dr. Brill used to say, the best models are the ones that combine the strength of human brain with computational power. So this is one of the framework where we allow the decision maker to put forward their preferences, and at the same time, we are also using the computational power that we have for generating a bunch of different options. And to end this lecture, I just like this quote a lot from my PhD advisor. He said in one of his papers that perhaps the most useful deliverable from all of this uncertainty analysis or model-based analysis is not a set of projections, but rather a tool for exploration that allows users to interrogate the model. So that is all I have for this lecture. I have included all the references over here. You probably have all of them posted as your suggested readings. And that's all. I mean, I have one more slide about the literature, existing literature about modeling to generate alternatives. There are, as you can see, very few papers, but more papers are coming up in the last couple of months or 4
Yeah.
months.
Quite a few recent publications.
Yeah, but in general, all of these papers kind of try to find out why the cost optimal solution might not necessarily be the best idea, and how just changing small things in the model can drastically change the model results. Okay, so that's all I have for this lecture, maybe a little shorter than I expected. But yeah, if anybody has any questions or suggestions or comments, I'm happy to talk about it.